Good afternoon, everyone. Today I present our recent results on the simultaneous sensing of two physical parameters. In our case, temperature and water vapor concentration, but still the concept can be extended to detect another physical parameters. The idea, or conventionally in literature, in order to measure two physical parameters, you need to have a physical sensor associated with each one of these parameters. In order to measure temperature and humidity, you need to have a humidity sensor to measure the humidity and thermometer to measure the temperature. And in some cases, you have to have a reference capacitor to cancel the effect of the temperature on the humidity sensing. In application where the temperature change affect the reading, you have to have two identical devices and rely on the differential signal to cancel the effect of temperature on your readings. Recently, in resonator-based sensors and application, the different mode of vibration started to attract attention, where researchers started to think of each mode of vibration as a different channel for sending information. For example, here, in order to determine the position, the velocity, and mass of a moving particle inside a microcantilever resonator, we need to rely on the four modes. Previously, in our previous work, we showed that using two modes of vibration, we can determine the position and the amount of mass on the resonator surface. Okay, now, what is the trend in literature that use two physical sensors to detect, each one of these parameters will increase the device size, will put more demand on the power consumption, and increase the fabrication cost of these devices. In this work, I'm trying to use a clamp microbeam resonator. This resonator are functionalized with metal organic frameworks, which is a selective material towards water vapor. And this resonator has to be operated in air for practical application. And we will use the first two modes of vibration to sense these two physical parameters. As a background slide, any mechanical resonator can be modeled as a stiff spring mass system, where the resonance frequency is square root of K over M. Now, once the excitation frequency matches the mechanical resonance frequency, you will get a resonance peak. Now, once the mass starts to get absorbed on the resonator surface, the total mass of the system will increase, and hence you will get a frequency shift. The frequency will go down. Now, this frequency shift can be used to quantify the amount of mass that is being absorbed on your resonator surface. Now, this mass can be of any pathogen, any bacteria, and any virus if you use a biorecognition layer on the resonator surface. Can be the mass of adsorbed gas molecules if you use a thin film that has affinity to that particular gas, pure interest. In this work, we are really interested in electrostatic actuated resonator, because for their known advantages of low power consumption, ease of fabrication. However, the challenge in electrostatic actuated resonator that they have low quality factor when they operate at atmospheric pressure due to the squeeze fin damping effect, which is simply the air molecules being trapped between the moving electrode and the lower electrode. Now, from simple mechanical theory, we know that any microbeam will have infinite number of modes of vibration. Mainly, researchers are concerned with using the first mode because it's the easiest to excite. Actuating the higher order modes is challenging and require high voltages to actuate them. In previous work, I showed that how we can use, different lower electrode configuration, that we design the lower electrode in a way, to some extent, matches the mode shape of vibration, and hence we showed that we can use half electrode to excite the second mode, and 2/3 electrode to excite the third mode of vibration. Now, another advantage that comes when you excite the higher order modes, or you operate the resonator or the sensor at these higher frequencies, that you will get higher responsivity. As you can see from the responsivity relation here, it's really directly proportional to the frequency. Increasing the operating frequency will lead to a highly responsive resonator, and hence you can detect really small amount of gas concentration or temperature. Now, as I said before, in this work, we are really interested in exciting or tracking the frequency shift in the first and second mode of vibration due to the change in the environmental temperature and water vapor concentration. Now, to demonstrate the concept, we start with a simple beam equation, where the amount of mass being absorbed on the resonator surface is simply the small m here, and the change in the temperature is the delta T. Now, without going in details of the analytical, we solve the corresponding eigenvalue problem using one mode Galerkin, and we end up with this relation, which is a closed formula for the first mode frequency and the second mode frequency. The only unknowns in these two equations is simply the temperature and the amount of mass being absorbed on the resonator surface. Now, in theory, we should be able, if we experimentally measure the frequencies of the second and first mode, using these two equations, determine the temperature change and the concentration. However, this is not the case in gas sensing. In gas sensing application, at particular temperature and at particular gas concentration, this is the amount of gas being absorbed on the resonator surface. Now, at the same concentration, if you increase the temperature, some of these molecules will have enough energy to escape from your coating material, and hence you will end up with less mass absorbed on the resonator surface at the same concentration. And this will cause error in your reading, on your results. However, if we look at the ratio of these two frequencies, we can see it is a function of the temperature change only. So by experimentally tracking the ratio of these two frequencies, we can determine the temperature change and hence use any of the previous equation to get the amount of mass absorbed on the resonator surface. Now, as you can see here, this is the eigenvalue problem plot. If you look here at the ratio equation, it clearly shows that increasing the temperature will change the ratio, and for any temperature value, if you change the mass, the temperature should stay constant. Okay? Now, this is the experimental setup that we use to characterize our resonator. We use two flow meters. One controls the saturated line flow, and one is controlling the dry line flow. The ratio between these two flow controllers will determine the gas concentration being supplied to the chamber. We use a lab view and data acquisition card to generate our actuation signal, which is composed from the two frequency components. And we use a photothermally controlled chamber to control the temperature inside the chamber. And to record the amplitude of vibration or track the shift in the frequency, we use a laser Doppler vibrometer to measure the change due to the change in the physical parameter. Now, to experimentally demonstrate this concept, we started by fabricating a clamp microbeam device. The device is composed simply from polyimide layer coated with metals from bottom and top, and functionalized with metal organic frameworks. Now, metal organic frameworks is simply a porous structure that has copper atom connected with organic links, and the pore size and the inner functionality will determine the selectivity of this material towards water vapor, which has been tested previously in the picture. Now, we perforated the lower electrode here to provide air path for the trapped air molecule to escape, so to reduce the effect of squeeze film damping, and hence we can see a moderate quality factor when we operate this resonator at atmospheric pressure, which is really an essential requirement for any gas sensing application, that you need to operate the resonator at atmospheric pressure, not inside vacuum chamber or controlled pressure condition. And this is the SEM image of our fabricated clamp microbeam. The inset here shows the uniformity of the MOF coating on our resonator surface. Now, as initial characterization step, we start with the white noise test, where we actuate our resonator with a white noise signal that has frequency component from DC to 1 megahertz. Whenever any of these frequency matches the mechanical resonance frequency, we will get a resonance peak. By scanning the vibration at different points along the beam length, we can see the clamp microbeam mode shape. This experimentally extracted mode shape matches the theoretical mode shape of clamp microbeam, which will give us indication on the uniformity of MOF coating. Non-uniform coating will induce distortion in the mode shape, and torsional component will start to play in. Another important test that we have to conduct here is to do frequency sweep around the mode of interest. So we did near the first mode and second mode at different actuation voltages. And this is really important to know the suitable voltages that we need to use to actuate our device and get a high signal to noise ratio that we can use it in sensing, and know our limitation of voltages so we don't bend the device by overloading it or over actuating it. The last plot here shows the multimodal excitation, where I fixed one source near the first mode and swept the other source near the second mode. Now, as you can see here, increasing the VSC voltages of the first mode will help in increasing the floor of the higher order modes of vibration above the noise floor, which is an essential requirement for sensing to have a high signal to noise ratio. Now, these are the experimental results that we will use here. So, we started our experiment by exposing our resonator to different water vapor concentration at room temperature. As you can see here, the second mode frequency shift is higher than the first mode, which is due to the higher operating frequency that we used under the same concentration value. We can see here, after flushing the chamber with nitrogen towards the end of the experiment, we almost returned to the original state. Now, when we increase the temperature of the chamber, you can see at particular concentration, we started to measure less frequency shift compared with the one that is atmospheric pressure, at room temperature, I mean. So, which is a clear indication of how the effect of temperature increase on or the evaporation effect on the resonator reading, on accuracy of your resonator reading. Even if we increase the temperature further, we still can see the reduce in the frequency shift at the same concentration value. For example, if we take the 6,000 ppm here, it's 3 kilohertz here, it's 4 kilohertz here, and almost 6 kilohertz here. So you can see dramatically the change in your reading when you increase the temperature of your chamber. Now, these are the summary of the results. Again, here you can see at 22, the frequency shift is higher than the one at 38 for the same concentration, which is a clear indication that the temperature effect is really reducing the amount of mass on the resonator surface. Now, one should not hear that, in contrast to my theoretical expectation that the ratio should stay constant, here I can see a slight deviation in the ratio reading that we got experimentally. And this is attributed to the thermal drift in the resonator itself, that we did the experiment over 3 or 4 hours, so there's a large thermal drift in our readings that affected the ratio reading. But still, if we take a case study where the frequency near the first mode was 180 kilohertz, and near the second mode was 290, and this is the corresponding ratio. Now, by taking the intersection of the arrows with the different calibration curve, we get the 3 possible solutions, which in the first mode case, these are the numbers, the second mode, these ones, and this is the ratio. Now, the only common solution for the 3 different scenarios is the combination of 45 degrees Celsius at 1,750 ppm. So though we were having a problem of thermal drift that affected our ratio reading, but still we can measure the 2 physical stimulus, which is temperature and water vapor, using this technique. In conclusion, we presented a new technique to measure 2 physical stimulus. To demonstrate the concept, we use temperature and water vapor, but it can easily extend it to detect another physical parameter. And if we could optimize the resonator device to excite higher number of modes, we can extend this method or technique to detect multiple physical parameters simultaneously, which will help in reducing the device size, fabrication cost, and the power consumption. Thank you.